Okay, so thank you very much, everyone, and my thanks to the organizing committee who invited me to come and give this talk. This is certainly an honor to present and to be able to try and paint a picture of what we're doing in supercomputing, what supercomputing looks like now, and how that relates to LLVM, and how we're planning on moving LLVM forward into the future in order to meet the needs of the future of HPC. Okay, let's see if this works. Aha! Okay, good. So the first question I'm going to try and answer is, what is supercomputing? And I'm going to define it roughly this way. It's computing for large, tightly coupled problems. And that means that the problems are large, right? It means that you need a lot of compute capability in order to solve them. And normally you need a lot of memory as well. They're tightly coupled. That means that the things doing the computing have to be connected using some kind of high throughput, low latency network. And beyond that, and so this is the core challenge in some sense of supercomputing, is to be able to put all of these things together in a way that makes sense. Slides out of order. Okay, so modern supercomputing is more or less divided into two camps these days, two hardware directions in a sense. One we have these many-core CPU systems, and in the other camp we have GPU-based systems. Now, the interesting thing about this is, we have now to do a lot of application development, and we have to figure out what this means. But first, let me just sort of give you a sense of where supercomputers are today. Okay. So here I have a chart that shows sort of current systems here, and then future planned systems over here. And let me just point out a few things on this chart. So one is, so this is the system that sits some tens of meters from my desk, and it's in the data center, and that has it's a 10 petaflop system. Our upcoming system in just a year or two is going to be 180 petaflops. So that will have increased by 18 times. But there's only a 2.7 times increase in the expected power usage. So this sort of underscores perhaps the challenge here in a sense. The other thing I'll point out is that the number of nodes is roughly the same. So we have about 50,000 nodes now in that system, and we'll have about 50,000 nodes in the next system as well. But if you look in this column, describes a future GPU-based system that's going to end up in our sister laboratory at Oak Ridge in Tennessee. And this system has only about 5,000 nodes. So even though they're both very similar in terms of raw capacity, and they're quite similar in terms of power usage as well, the way that you program a 5,000 node system at that scale and a 50,000 node system at that scale are quite different. All right. And so going forward, we're trying to get to exascale, right? So we're trying to get another factor of 5, and we're trying to do it on a fairly short time scale. So here we have, this is our plan of record, I suppose you might say, and the thing I want to point out here is that this is where we have our first exascale systems appearing on the roadmap in fiscal year of 2021, which in some sense sounds like a long time away, but given that we normally have about a 5-year development cycle for each of these systems, it's not that far away. And we really end up having to start thinking now about how we're going to prepare our applications, our software, our tools for these systems. And so, as I said, so this is a 5x increase, but it's less than 5 years. And so here we are. And now I'm going to describe what we're trying to do, what this line means here, and how this relates to LLVM. Okay. But let me just back up a bit and show you what that dot actually indicates. So it's an exascale system. Okay, so This is our definition of exascale in some sense. But the other things are also sort of interesting. So the target power budget here is 20 megawatts for the full system. So remember the 180 petaflop system wanted like 13 megawatts. And so now we want to increase that by a factor of 5, but we only want it to take 1.5 times the power. Okay. So what we want is the ability to have applications that can run on the many-core CPU-based systems and on the GPU-based systems. And we'd like them to be able to run well. We want to have a single maintainable code base for these applications, but we want them to run with reasonable performance on both of those systems. Let me also talk a little bit about memory, since if I talk only about the compute, you only see half the picture in some sense. So modern systems here, and this is true both for the CPUs and the GPUs, the memory hierarchies in some sense are becoming more complicated. So here's the compute, and then this is a cartoon, but nevertheless, the idea is that the memory here, you have this sort of on-package memory, which has, well, here it says it's 5 times the bandwidth in this case, of the off-package memory out here. So there's a large capacity out here, and then there's smaller capacity but higher bandwidth stuff near the compute. And how we deal with this is going to be sort of an interesting thing. For the Intel Knights Landing cores and the future ones in that line, there's also sort of an interesting configuration choice that applications have, because they can choose to use that high bandwidth memory either as a cache for the main memory, or they can map it explicitly, so they can then use either the off-package memory or the on-package memory explicitly, or they can do some combination of both. And the interesting thing is that the GPU-based systems look very similar now. So now we have the GPU-based systems are coming out with unified memory, so they also have a sort of unified coherent address space. And so the way that you program them is now also different. So you can, I should say, instead of saying, well, to go from a CPU-based code to a GPU-based code, you have to change your malloc calls into special things, and you have to keep track of which data is where and maybe move it explicitly or not. Now we just have unified memory. So the memory allocation is the same. You don't have to do anything special. You can, if you'd like, let the hardware just sort of page the memory back and forth for you between the CPU and the GPU. So this is nice, at least in theory, although how we actually manage this is going to be interesting. Okay. So as I said, the goal was to get this thing called performance portability, right? We want to have applications, we want to be able to maintain them reasonably and have them run with high performance on these various different systems. Okay, so how are we going to do that? Well, we have this division of responsibilities. So here we have the high-level things, applications and solver libraries and such. So they're responsible for some piece of this. Then we have libraries that we use to abstract memory and parallelism. They're responsible for another piece of this. And then we have compilers and tools, and they're responsible for, well, the rest of it, I suppose. Okay. But I did want to point out, because I'm not really going to talk about this and dwell on it specifically, but I do want to point out some of the things that fit in this box. So applications and solvers and such, they have a number of parameters that they can often expose algorithmically that are really important for adapting to different architectures. These are things that no compiler or low-level abstraction library is ever going to do for you, like changing the kind of basis functions that your solver is using, or making kind of resolution versus accuracy trade-offs, and a whole bunch of other things. So it's really important for the applications and the solvers to be parameterized sufficiently, or else in some sense none of the rest of this really works. But so long as they are, then there's a lot we can do. Okay. So what are people using now? How do codes look? So I want to say something about what's going on now, and then how things are going to go forward. So this is some survey results. This is from 2015, and I'll just point out a couple of things. So in 2015, in our HPC environments, about half of the codes were using OpenMP to express parallelism on the node, and a small minority of codes, there's a couple of these in this list, we're using abstraction libraries on top of that, like Thrust or TVB, something like that. I'm not saying TVB runs on OpenMP, but I'm saying that the number of people who were using sort of C++ libraries to handle that abstraction was actually a fairly small percentage of the overall total. But this is really changing. So now we have a number of good options, and we're actually investing quite a bit in developing these. So here, I just want to show you a little bit about what this looks like. So here we have examples from 2 different libraries that are being developed as part of our Exascale programs. This one's called Raja, this one's called Cocos. They're both freely available on GitHub, as you can see, so feel free to try them out. And here I'll just sort of point out some very generic features of these libraries. Does this work? Aha, yeah. Good. So one is, here we have C++ lambda functions. So we're using C++ lambda functions. And the other thing is that we're using some kind of abstraction here. And OpenMP and other compiler directives, compiler-assisted things, sit under the hood of most of these abstractions at this point. And the idea is to be able to take advantage of A, good programming practice, but B, also take advantage of the fact that if the compiler understands what's going on, there are things that it can really do to help you. And so we want to get the best of both of these worlds. Okay. And the other thing I'll point out is that it's not just these sort of custom libraries that are providing us with these kinds of features now, because at least starting with C++ 17, the standard library has a whole bunch of different parallel algorithms. They threw everything in the kitchen sink, I think. So we'll have to see how well this works out. But I mean, for a number of these things, this for each is in here, right? And that's the standard workhorse, I suppose, of most of these things. And there are reductions and other things. So for example, in modern C++, or soon to be modern C++, you'll be able to take what you would think of as one of these regular algorithms and just kind of tell the library, oh, by the way, please parallelize this, or maybe vectorize it, or something like that, and some magic's supposed to happen. Okay, but now we have to figure out how to make the magic actually work and work reasonably. And the other thing I want to point out that's really important about these abstraction libraries is that the abstraction libraries don't just deal with parallelism. Many of them also they deal with memory as well. So what and the memory is in some sense the harder part of the problem for a pure, say, compiler-based solution to address, because it's really hard for a compiler to rearrange your data structures and everything, especially because of ABI considerations and lots of other things. But with the library, the programmer has enough control in order to be able to give good sort of policy-directed guidance. So here, this is also from this Cocos library. I'm just sort of pointing out here that you can tag a particular variable or view of data or what have you as you can give it a type. So here it's saying, okay, this is a constant read-only view, and I'm going to access it randomly. And then the library can go, oh, okay, assuming it's small enough or what have you, this thing is going to end up on the GPU in texture memory, and the performance is going to be much better than if it just sort of mapped it to some default location in global memory. And so here, this is just from a sort of old presentation at this point, but the idea is to show you that doing this makes a big difference to performance. And this is essential. The fact that you can change the memory mapping and layout and such for each of these different architectures has a big difference on every architecture. But it's biggest on the GPU, but it's important on all of them. Okay. So where does this sit? So our development plans for future systems, as I said, they cover all of these different areas, and so we're investing in updating these applications to use these abstractions to become more parameterizable, to adjust to new architectures. The Department of Energy currently is focusing on about 30 of these things between applications and solver libraries. Then we also have these abstraction libraries like Kokos and Raja that I pointed out. And then we have a whole bunch of projects focusing on compilers and tools. All right. So now we'll talk about LLVM. Okay. So the first thing I'm really excited about as a result of this project is we're getting a whole bunch of people who have been playing with LLVM or sort of doing some LLVM projects or were interested in LLVM, and we've been able to get them onto this project, and so we're now working on bringing up a new kind of generation of LLVM developers within the Department of Energy and partner institutions. And we're doing so all over the United States. So I very roughly drew these circles, but this is roughly where they are. And so this is I actually think this is really exciting. I have a new set of colleagues. I'm going to highlight at this point a number of the projects that we're working on, and sort of explain how LLVM fits in. Some in more detail than others. So, so the first project, which I'm not really going to talk about in too much detail, but you can visit its website if you'd like more information, is ROSE. ROSE is a source-to-source transformation toolkit for code. And it now has two ways that it ties into LLVM. One is that it can use Clang as the front end. And so you can parse C++ code or OpenCL or what have you with Clang and feed it into this AST. ROSE's AST has been specifically designed for doing complex transformations, and so it does this sort of AST to AST thing. And then at the end of the pipeline, ROSE can actually generate LLVM IR. So you can sort of use it as a poor front end for a whole bunch of different things. But the main reason that they generate LLVM IR actually is to support instrumentation. So some of these transformations actually are instrumentation-based tools. And so a lot of instrumentation is very easy to do at the LLVM level, and so they have this capability to generate LLVM. Okay. Another project which is relevant here is our autotuning project. So as I mentioned, it's really important for applications to be parameterizable, and this enables them to be adjusted to different architectures. Okay, that's easy to say, but then you say, well, now I have a whole bunch of parameters, so what do I do with them? And so there have been auto-tuning tools out for a while now, but we're really trying to focus now on putting together tools, taking from existing technology, but putting together tools that can really be deployed in production environments. And so now we have this YTune project, which is it's a combination of machine learning assisted search and optimization over this parameter space, which includes both application tuning parameters and also compiler directed tuning parameters as well. And specifically within the scope of this project, we're going to be working on enhancing LLVM both in terms of getting better optimizer feedback in cases where that can help direct the auto-tuning search, and also putting in whatever sort of tuning hooks we find are useful to be able to have the auto-tuner direct the optimizer in various ways. So so this is really quite useful. And the other sort of thing that's interesting here is that this tool has the ability to do sort of application-specific optimizations. So if you have, there's an example here which I don't really have time to explain, but they can do some really neat things. For instance, when you have adaptive mesh refinement code, they can integrate the parameters for the adaptive mesh refinement box sort of iteration algorithm with the polyhedral optimizer that they have inside this tool. And then they can optimize both the loops inside the partial differential equation evaluation engine, but also the algorithm outside of that that's iterating over the boxes. And then they can do some cool things like that. So, okay. The next thing, next project I want to highlight is our OpenMP Focus project. So we have a project which is sort of all things OpenMP in some sense. And it has a number of cool things in it that I'm pretty excited about. So first, we have a focus on improving our OpenMP code generation, which I'm going to talk about a lot in a couple slides, so I'm not really going to focus on that now. We have focused on improving the OpenMP runtime library, and also using Clang and the rest of it to prototype new features in OpenMP. So I think the lesson that we should learn from experience is that it's a really bad idea to standardize things you haven't implemented yet. So this is really our focus going forward, is that the features we propose to add to the OpenMP standard are things that we should actually have implemented and tested and shown are useful. So this project has that specifically as part of its charge. And but before that, I do want to mention a little bit about the runtime library piece, because I think this is kind of neat. So we have a group that's taken LLVM's OpenMP runtime library, which normally sits on top of pthreads or system threads on whatever system you're using, operating system threads. And they retooled it a bit so that it can sit on top of this library called Argobots, which is a lightweight threading library that's developed at Argonne. And they came up with this thing that they call Bolt, which they're really excited that they found a recursive acronym for it. And but it's actually quite neat. So unlike the sort of stock LLVM runtime, OpenMP runtime, which works essentially the same way as all other OpenMP runtimes in that they sit on top of pthreads or the system equivalent, this version actually handles nested parallelism very efficiently. And handling nested parallelism very efficiently is really important, because nested parallelism normally comes when you compose libraries or other pieces of code. And the fact that most OpenMP implementations don't really handle nesting very well means that it's really difficult to compose libraries and other pieces of code that use OpenMP. And people have there are changes that have been made to the standard to make this easier. The argument that the Bolt team has been making for a while now is that actually this is a runtime problem, and we could just fix the runtime and make this better. This is mostly true. So like with any other lightweight threading library, it works really great so long as you don't have any blocking system calls in your threads. But aside from that, here I just want to show you they have, this is cut off a bit, unfortunately, but there's a small benchmark which I've sort of summarized here, nested OpenMP benchmark. And here you see the performance is the Bolt version is down here, and the kind of default threaded versions are here and here. And this is a log scale, so the Bolt version down here is significantly better, mostly because you just don't oversubscribe the threads on the system and various other things. Okay. So now, okay, so the last project I'm going to talk about is Proteus? Proteus? I don't know, something like that. I'm not sure how we pronounce this actually, so I'm not going to try again. But this is another sort of strained acronym, so I won't go over that. But the idea is that we're going to work on developing a high-level sort of an IR-level representation of parallelism, and use that to better optimize programs with parallel constructs. And we're also going to explore other things related to the memory hierarchy, like if there are interesting things we can do with non-volatile memory, which I'll say a little bit about at the end. Okay. So let me first try and motivate why, in some sense, we're looking at this. So I showed you all those neat libraries that we can now use to express parallelism, including the C++ standard library, which now has features that you can use to express parallelism. And the problem is, in some sense, that on most architectures, it turns out those ways of expressing parallelism aren't particularly good. So they end up, you end up with a lot of very small parallel regions. So you have a lot of kind of fork join sections in your code. And if you're not really careful about it, you can end up spending all of your time waking up threads, synchronizing, all that kind of stuff, and very little time doing the work that your program is actually trying to do. And the problem in some sense is that there's a impedance mismatch between the way that programmers sort of want to write code that expresses this sort of encodes a separation of concerns, where different libraries take care of different pieces and different functionality, and the fact that when you run on actual hardware, you often don't want the code to really run that way. I suppose it's analogous in some sense to having code which is very nicely written and structured and maintainable, but uses virtual functions everywhere and doesn't perform very well because your processor spends all of its time dispatching indirect function calls. So how are we going to deal with this? So here I just sort of schematically said what I indicated what I said, which is, okay, so I have one library that has this parallel for each, and I have another library that has the function of the parallel for each, and I call one right after the other. And if you just sort of naively implement this, then you may spin up or wake up a bunch of threads to do something which may not be that big. Then you're going to shut them down again or put them to sleep, and then you get to the next function and you do it again. And this is not really what you want the code to do. This perhaps is especially true if you're running on non-CPU hardware, or maybe if you are running on CPU hardware. In any case, so there are a number of transformations in some sense that you would like the compiler to be able to reason about on this kind of code. So here I have indicated this. So here so if you have this parallel for loop, for example, maybe depending on the hardware or maybe how much data is in here, or what have you, you may want to split this into two separate regions. Or maybe if you started with two separate regions, you would actually want to combine them into one region. And then if you have two separate regions, well, depending on how this is implemented or what have you, you may actually want to have one parallel region that just has the two work-sharing constructs inside it, instead of having two separate parallel regions. And you can think about on a GPU, these things may be individual kernel dispatches. On a CPU, these are implemented normally with just threads. But the idea is that depending on how you structure this and how it gets implemented, you would like the compiler to really be able to reason about these things. This ends up being fairly important. Okay, so let me talk a little about sort of where we are today and how we can move forward to a place where we can actually solve that problem. So right now, the way that we have OpenMP implemented in LLVM is we use this early outlining approach, right? So when Clang sees this OpenMP pragma, it turns it into some set of function calls. So it takes the loop body here and puts it into some function, and then there's a runtime call which takes a pointer to that function and a bunch of other parameters and runs this thing in parallel. And so this has a number of issues. One is it's really difficult to do any of that splitting or merging or anything else that I indicated on the previous slide, because all the optimizer gets to see is some collection of function calls. And the other problem that we have is that in the body of this function, you're missing all of the context from the parent function. So there are pointers. You're missing pointer aliasing information. You're missing information about the loop bounds, because of course there's no loop anymore. There's a whole bunch of other stuff you're doing. But aside from all of that, in some sense, there's an even larger problem, which is that we've decided really early what to do. We decided what to do before we did any analysis, before we did any inlining, before we did anything. We just sort of did a pure syntactic transformation, which is fine functionally, but doesn't really get us what we want. Okay, so let me sort of explain one of the sort of largest problems with deciding on this too early. Okay, so OpenMP has these target directives, which are used to address accelerators. So like a GPU or what have you. But you can use them on CPUs as well. And so here I have this target region. And I'm going to pretend that this is targeting a GPU. So this is what the compiler sees: target region and a function call. And inside the function call, I have this parallel for loop. So this is a very common situation, especially with these abstraction libraries and everything else in the way. And so what happens here? Well, if you have to do a purely syntactic transformation the way we do right now, what does this mean? Well, I have a target region, and then I have some serial code, and then I have something, and then I have some serial code here. And the front end doesn't know what that function does. So you have to use some scheme that supports running serial code, because this function could be serial code too. You don't know. But GPUs don't really run serial code that way. Right? On a GPU, you start up a whole bunch of threads, and they do something, hopefully all together. And this code is actually doing that. But the front end can't see that. And so it doesn't do anything that's anywhere near reasonable in some sense. It has to encode a GPU kernel for this that has this built-in state machine. So that all the threads start, but then only one of them there's a thread that handles this serial region, and then it handles this one too. And you have all these states that get encoded, and all of this uses extra registers and a lot of resources and all of that stuff. And the programmer doesn't really understand why the compiler just can't do the right thing. So we want to make the compiler do the right thing. Okay. So how might we do this? So here, instead of having the front end generate this function call stuff directly, one thing that we're trying to investigate, and if you're watching the mailing list recently, you may have seen some discussions related to this, is to have some kind of IR level representation of these parallelism constructs. And I'll just sort of point out that a couple of reasons why this is tricky in some sense. So if you just sort of pretend that it looks vaguely like that in some IR way, there are a couple of things that these like region markers here would have to have some kind of magic properties. So here are some of the magic properties they may need to have. They may need to keep stack allocations that are in this region from going out of the region. Because if I have a stack allocation in here on every thread, I certainly can't turn that into one stack allocation on one thread. You need to make sure that these markers somehow capture and otherwise do things to the pointers that are visible in this region. Because A, the region can run multiple times. B, the region may actually run after the function returns, depending on the semantics of the thing that you're lowering. And for loops, you also need to make sure the compiler doesn't introduce any additional loop carry dependencies. No secondary induction variables, anything like that. Because induction variables here are actually special, because they interact with the runtime. And so as I said, so these things have to have some magic properties. And we're currently trying to figure out exactly how you would encode these so that they interact well with the rest of the optimizer. But the last thing I want to point out is that if you remember, we're using these libraries. These libraries use lambda functions. And so the lambda functions, in some sense, replicate a lot of the same problems that we have with the OpenMP constructs. Because they also turn into early outlined function bodies that we then get pointers to. And those end up getting fed into things that dispatch on threads and such. So if we only solve this for OpenMP, we can do some things, but we don't actually get a lot of the benefit. We also need to handle C++ lambdas in such a way that lets the optimizer see what's in those, so that we can lower things through the runtime and the analysis in a way that's helpful. Okay. So the groups that are working on this have there are some past prototype work that they've done, which is sort of interesting. Some of it's available on GitHub, and others of it is not. But here there's this OpenArc compiler, which is a sort of researchy front end for LLVM that this group at Oak Ridge created. And here they have a bunch of programs, and they were doing some experiments to see how much these sort of architecture-targeted sort of higher-level optimizations help the ones that they've been able to implement. And these are things like using shared and local memory on GPUs and other sort of analysis-based transformations. Now, and so the point of this plot is simply to answer that question by saying a lot. So if you do the right thing, or perhaps I should put it another way, if you do the wrong thing, performance can be pretty bad. And the performance between, say, an NVIDIA GPU and an AMD GPU are much more similar than taking that same kind of setup and trying and running it on an Intel core. Okay. And the last thing I'll point out, only because it's different, is this topic of what to do with non-volatile memory. So the one reason that it's different is because it's not really in any way specific to HPC. In fact, there are more uses of non-volatile memory not in HPC than there are in HPC. But the other thing that's true is that as we move forward, the technology space for this means that that large capacity memory that HPC needs in its systems is going to be most economically provided by non-volatile memory. So we're likely going to start ending up with systems that have large amounts of non-volatile memory in addition to the sort of high bandwidth memory, which looks more like DRAM perhaps. And then so the question is, well, do we actually want to do anything with the non-volatileness of the memory? Or is it just kind of like larger, cheaper, slower-ish DRAM? And I don't think this question has been decided yet. We don't really know, but we've started constructing some prototypes to try and figure out if there are sort of programming language level things that you might do in order to take advantage of the fact that it's really easy to now just sort of take stuff in memory and have it persist. And there's a prototype which I think the link to how to get it is here. I think it's on GitHub someplace. And so there's been some experiments with introducing some pragmas and some language extensions in order to see how you might program this in this way. Okay. So in any case, I put this up only because some of you may have actually worked on this kind of thing, and if you have ideas, I'm certainly interested in hearing them. I haven't yet heard a spectacular argument for how we would end up using something like this, but we're trying. Okay. So let me conclude. The first thing I want to say is the future of HPC looks quite diverse. People have thought for a long time that, well, right now we have lots of different HPC architectures, CPUs and GPUs, what have you, but that's really kind of a fad. And going forward, things are really going to converge on something. But of course, like in many other cases, like everyone thinks that, but no one agrees on what the something is. So we don't really have a something we're converging on. The future actually looks more diverse than the present state. And how we adapt our applications to that is going to be a really interesting challenge. Second thing is that responsibility for this adaptation is really split over a number of different areas. It's not just the compiler, it's not just the library, and it's not just the applications. I think the thing we've realized is that we really need to adapt all three of these areas. But relevant to us, there's a lot of compiler work that needs to be done in order to make the other two pieces really work the way that they should. And the third thing is that, well, the thing I just said, but moreover, we're actually working on doing this. And this I think is really exciting and should be a lot of fun. So with that, thank you to everyone, thank you to the organizing committee, and thank you for your attention.
Hi, thanks for the nice talk.
Thanks.
So regarding the focus on the Rhino part, some of the language constructs look very similar to C++ AMP. Can you comment on that?
Yes, they are. I don't know a huge amount about C++ AMP, but from what I've seen, yes, it's also a very similar kind of setup. With the parallelism, you put in lambdas. I think they share a lot of the same, a lot of similarities.
Thanks for the talk. You mentioned you proposed to switch from early outlining to late outlining. Yep. But do you think that outlining is a good approach at all? Maybe is it possible to do all the parallel work just in place?
So you know what's funny is until a couple of months ago, I actually didn't know of any compilers that did that, but I do now know of one. There is a compiler that actually lowers parallelism like that. Its runtime, instead of taking a function pointer, actually takes a bunch of pointers to code locations and kind of jumps around the code while it does this. I don't see any real fundamental advantage to doing that because at least on a CPU system, the overhead from part of what you're adapting for in some sense is the overhead from the dispatcher and the function call. But the parallel dispatching, the overhead from that is much higher than the overhead from the fact that you've outlined the function itself. And on a GPU, you need to separate the code somehow anyway because you're going to generate GPU kernels and such for the pieces that you're running on the GPU. So I think representationally, it does make sense to sort of separate out the functions at some point. But you just don't want to do it too early. Does that answer your question? Yeah.
I enjoyed the talk.
Thank you.
So libraries, abstraction libraries like Trilinos and Focus, in some sense, since you're layering them on, even though you're layering them on top of OpenMP, it seems to me that they could do a lot in addressing the performance portability problem by really customizing the code they write internally for different platforms. And so what I'm wondering is how much is really left to the compiler? I would like to think that the compiler still has to do a lot, but could they really tailor, for example, the OpenMP or CUDA or whatever they use internally for the platform so that they achieve a lot of the performance optimization goals and performance portability?
So they can. The thing that they can't do, being libraries, in some sense, is they can't do a good job of merging together constructs that are sort of separated in the source code. And they also sort of are hampered by any kind of optimization limitations that we have. As I mentioned, we currently outline lambdas too, and then we lose some of the optimization potential there as well. I'll mention just for context that if you have a lambda function and you're just using it in place, like you just have a lambda and you use it in one spot, right? Then the optimizer has no problem with that because functions that are only used in one place just get inlined, and so you just optimize it. It's fine, right? The place where you have problems is that when you take the lambda and you capture it and then you pass it off to some other thing, because then it just looks like a function to which you took a pointer, and the pointer escapes someplace. So the compiler doesn't inline that anywhere. It loses all of the context for that. But the thing is with Kokos and Raja, et cetera, you end up with the same kind of abstraction problems, right? So you would like the library to lower the parallel code into some kind of construct the compiler can understand. So it can then take parallel regions that come from different parts of your application or different libraries and merge them together or split them or what have you. And that's something that's really hard for a library to do. Kernel splitting is also something that's really hard for the library to do. And so there are definitely places where you'd like the compiler to be able to reason about what's going on.
Yeah, I think you may have just answered the part of the question that is to come. So I was really like this this early slide where you like talked about these shared responsibilities, and it seems that in like many, for most of the projects you then told us about, you spent a lot of effort on like dealing with this shared responsibility that happens early on, like very late in that sort of like pipeline of those two stages. Are you aware of any, or like what, any sort of like more high-level approach to HPC sort of like help with this? Are you aware of any projects or?
Sure. I mean, so.
Can you drive in that direction?
I mean, we have a number of projects that have like domain-specific languages that they use to generate code, and these actually come in a couple of different forms, right? So we obviously have projects that use domain-specific languages in the traditional sense. So there's some language, they have a little parser and things, and they generate code. We have quantum chemistry applications that use a lot of tensor contractions. There's this thing called TCE, the tensor contraction engine, which will generate all sorts of tensor contraction code. We also, more relevant to LLVM, we have a couple of projects now that use embedded DSLs where they looks like a regular embedded DSL. You have expression templates and all that kind of machinery. But what the templates actually do is they build up IR, which then gets JITted and executed. And this is actually really neat. I know of at least 2 applications that do this now. They're using it in some sense for 2 reasons. One, I suppose, is sort of the obvious thing. Like, well, like once you know the parameters and the sizes of things, you can JIT the code and it's more efficient. I actually thought that was the primary reason they were doing it. But when I talked to the application teams, they told me that was just a side benefit. So the real reason they're doing it is to get around abstraction problems. So because the libraries they have, if you just use regular expression templates and such, you can't optimize. Though, like the expression templates, they end at a statement boundary, right? You have a statement, and that's the thing you get to use in the expression template. And because of what they were doing, they wanted to have code that was in different statements that came from different parts of their library and their application. And they actually found that a good way of getting all this together and still getting the really high performance that they wanted was to have those statements just turn into IR and then JIT the resulting mass of code they got out than anything else. So I thought that was really interesting. But yeah, so I mean, there are these sort of more custom approaches, software that can start with a more mathematical description of what's going on, and you can generate code. There's a really neat project out of Carnegie Mellon, maybe, Spiral, that has a really neat sort of advanced code generator for different kinds of algorithms as well. But the problem is these all end up being limited in domain. So they work for some subset of projects, but in the end, we have general purpose programming languages because they're general purpose. And I.
Will the domain users have to use them?
The DSLs? Sometimes. So, I mean, the problem with DSLs often comes down to maintenance, right? I mean, like, you have some grad student or something who goes and makes this nifty little code generator. That's fine. 15 years from now, who's going to know how to update that thing? And this often turns out to be a very large practical challenge.
We've got time for one more question.
You mentioned fortran on a couple of slides. Can you give us an update on that?
Sure. So, okay, so our effort in the Fortran area right now is focused on our partnership with NVIDIA, PGI, who are working on preparing their Fortran front end to be open source. They have a prototype of this, development branch of this that they're working on, and I don't want to preempt their announcement, but It should be coming out pretty soon. It will generate LLVM IR. There will be an LLVM front end.
Okay, so then thanks, Helligan.
Thank you.